Ever wonder how distributed systems reach consensus and coordinate seamlessly, even in the face of failures? Imagine a network of interconnected nodes, each making decisions independently yet in harmony. Trust emerges from chaos through protocols and algorithms that ensure agreement and safety. Picture this intricate dance of communication and validation, where resilience is key to keeping the system in sync. In the world of distributed systems, collaboration reigns supreme, steering towards a common goal despite the challenges. Consensus and coordination, pillars of reliability in the digital realm. In the complex world of distributed systems, the challenge of achieving consensus among multiple computers is paramount. When servers crash, networks falter, or messages go astray, the need for a unified decision becomes critical. Enter consensus algorithms, the bedrock of reliable distributed applications. They ensure that even in the face of server failures, all systems can align on a singular value or choice. Imagine electing a leader server, committing database transactions, or synchronizing configuration changes seamlessly across a cluster. These real-world examples underscore the importance of consensus in maintaining consistent, replicated data. In this landscape of interconnected technologies, consensus isn't just a luxury, it's a necessity for operational integrity and continuity. Imagine a world where messages vanish in thin air, servers go silent without warning, and chaos reigns. Network failures disrupt communication, leaving servers clueless amidst crashes and slowdowns. In this digital turmoil, split decisions sow seeds of confusion, with conflicting server actions leading to data mayhem. We need systems that can weather the storm, ensuring smooth operation even when servers fall. To navigate this coordination challenge, let's explore solutions that promise resilience in the face of uncertainty. In the world of distributed systems, Raft shines as a beacon of clarity and simplicity. Designed as a more digestible alternative to the complex Paxos algorithm, Raft offers robust safety guarantees without the headache. Picture this: servers unite to elect a leader, a central figure entrusted with steering the ship of decisions. This leader dutifully replicates commands to followers, ensuring synchronization across the system. And here's the clincher: once a decision is locked in, it's etched in stone, never to be lost in the turbulent seas of data. Raft's mantra? Stability and predictability, wrapped in a user-friendly package. Ever wondered how Raft works behind the scenes? Picture this: within Raft, followers cast their votes for a candidate who will serve as the leader. Should the leader fail, an election is triggered. Raft structures time into terms, each marked by an election and a new leader. These terms are crucial for servers to identify outdated information and ensure a single leader at a time. Think of it as a seamless relay race, passing the baton of leadership with precision. This dynamic system of elections and leaders keeps everything running smoothly, preventing chaos and maintaining order. Ever wondered how a Raft server navigates through different states to maintain a stable system? In the follower state, it dutifully responds to leaders and candidates, ready to transition to the candidate state if a heartbeat is amiss. As a candidate, it seeks votes from peers, striving to win the election or gracefully return to being a follower. Finally, as a leader, it takes charge, handling all client requests, sending heartbeats to assert authority, and ensuring log entry replication to followers. This dynamic interplay of follower, candidate, and leader states orchestrates the robust functioning of a Raft server system. In the intricate dance of Raft's protocol lies the crucial Chapter 3, leader election in detail. Picture this: a symphony of servers, each vying to be the conductor of decisions. How does this unfold? A follower, impatient for a heartbeat, steps into the spotlight as a candidate, claiming the term's throne and seeking votes. Others weigh in, and as the chorus sings, the candidate with the loudest applause takes the lead. Yet, the stage is set for drama with randomized timeouts, ensuring a decisive outcome. If harmony eludes them, a new election begins, ushering in a fresh term. In this ballet of servers, the goal remains clear: to crown a leader who orchestrates unity. Unlocking the enigmatic Paxos algorithm can be a daunting task. Unlike Raft, Paxos operates through proposers, acceptors, and learners. In the prepare phase, proposers seek acceptance from acceptors with proposal numbers. Acceptors, in turn, commit to not accepting lower-numbered proposals. Subsequently, in the accept phase, proposers present the value upon receiving promises from enough acceptors. The value is accepted unless a higher-numbered proposal interferes. Once a majority agrees on a value, learners are notified, solidifying the choice indefinitely. This intricate dance of proposals, promises, and agreements forms the core of Paxos's consensus process. Remember, in Paxos, once accepted, the decision is final. In the world of distributed systems, Raft and Paxos stand as two behemoths, each with its unique strengths and intricacies. Raft boasts a strong leader, funneling decisions through one elected figure, making it a go-to for beginners seeking clarity. Its sequential log structure and term-based approach offer a straightforward path to understanding. On the other hand, Paxos operates with symmetric roles, allowing any server to propose values, showcasing mathematical elegance amidst complexity. With a flexible structure and a reliance on proposal numbers over term boundaries, Paxos offers a different flavor of efficiency. Despite their differences, both algorithms ensure safety and progression with a majority consensus. When it comes to new systems, Raft often takes the lead due to its clear-cut nature. As a leader is elected in Raft, it takes charge of client requests by adding them to its log and sending them to followers for replication. This process ensures all servers maintain identical logs in the same order. When a client request comes in, the leader logs it and then swiftly replicates it to all followers in parallel. Pausing to ensure a majority of servers have stored the entry, the leader then commits it and responds to the client with success. This meticulous process in log replication guarantees data consistency and reliability across the system. Imagine a lease as a key to exclusive access, a time-limited agreement granting control of a resource, much like renting an apartment. Why bother with leases? Picture them as the silent coordinators, allowing servers to act independently within a set timeframe, free from interference. Should a server falter, the lease expires, smoothly transitioning control to another server. This seamless handover ensures automatic recovery without the need for intricate failure detection systems. In a dynamic system, leases play a crucial role in maintaining order and continuity, offering a structured approach to resource management. In the world of servers, leases are the key players. Picture this: Server A is granted exclusive access for a brief 30 seconds. During this time, it's in the spotlight, handling requests swiftly and independently. But as the clock ticks, a decision must be made: will the lease be renewed, or will it expire, allowing another server to step in? Leases offer a trade-off: speed at the cost of slightly dated information. Efficiency comes at the price of freshness. So, remember, in the realm of leases, decisions are fast and furious, but coordination is key once the lease expires. Freshness for efficiency, that's the name of the game. Ever wonder how systems ensure exclusive access to critical resources? Enter common lease applications. In distributed locking, a server's lease on a lock guarantees sole access, releasing automatically if the server fails. Similarly, cache consistency relies on data validity leases, allowing seamless requests until expiration prompts a refresh. And in leader leases, a leader's authority is proven through a lease, with followers trusting decisions without extra confirmation. These leases are the backbone of secure, efficient operations, ensuring smooth functioning even in complex systems. In Chapter 6, we delve into Zookeeper, a vital coordination service for distributed systems. Acting as a centralized hub, Zookeeper handles configuration, synchronization, and group services with ease. Pictures nodes as data nodes organized in a hierarchical structure, akin to a file system. Clients can set watches to stay informed of changes, while sessions maintain connections with timeouts for failure detection. This service extends guarantees of sequential consistency, atomicity, and a single system image for clients. Once an update is successful, durability is ensured. Zookeeper simplifies complex coordination tasks, offering a streamlined solution for distributed systems. Ever wondered how Zookeeper can revolutionize your system's reliability and efficiency? Let's delve into its practical applications. First, witness the seamless leader election process, where servers compete through ephemeral nodes for the coveted role. Next, imagine the simplicity of configuration management, ensuring uniformity across your cluster effortlessly. Then, picture the dynamic service discovery mechanism, enabling swift access to available services with ease. And finally, experience the power of distributed locks, granting exclusive access through a seamless node-based system. In a world of chaos, Zookeeper brings order and stability to your distributed systems. Ever wondered how the Zookeeper architecture juggles multiple roles seamlessly within its ensemble? Picture this: clients flock to the ensemble for requests, while followers diligently serve read requests and shadow the leader for replication. And who's the star of the show? The leader, of course. Handling all write requests and orchestrating consensus like a maestro. Zookeeper operates as a replicated service, akin to a synchronized dance, using a consensus protocol similar to Paxos for data replication. Clients have the liberty to connect to any server for reads, but writes must pass through the leader and gain approval from the majority before being deemed successful. In essence, Zookeeper's ensemble harmoniously ensures data consistency and reliability through a well-orchestrated symphony of distributed coordination. As we delve into Chapter 7, we explore the critical role of consensus algorithms like Raft and Paxos in fostering reliability within distributed systems. These algorithms enable servers to reach agreements even amidst failures. Picture a consensus layer where Raft or Paxos orchestrates unanimous decisions across all servers. Building upon this foundation are coordination services like Zookeeper, elevating the framework to provide advanced primitives. This sets the stage for your application to leverage these coordination tools, constructing robust distributed systems. By utilizing established coordination services such as Zookeeper, you can sidestep the intricacies of implementing Raft or Paxos, freeing you to concentrate on refining your application's logic. In essence, embrace proven coordination services to empower your distributed applications while sidestepping the complexities of consensus algorithm implementation. Consensus is the cornerstone of reliable systems. Distributed servers must agree on decisions, even amidst failures, ensuring safety. Raft simplifies this complex process with a clear, understandable approach, offering the same guarantees as Paxos through a strong leader model. Leases, based on time, enhance efficiency by enabling servers to act independently, automatically recovering when necessary. Utilizing coordination services like Zookeeper leverages consensus for leader election, locking, and configuration management. In building resilient systems, consensus, clarity, efficiency, and coordination are key. Let's put our understanding to the test with a quick quiz on Raft server states and functionality. Question 1. Can you name the 3 states a Raft server can be in and explain how a server transitions from follower to candidate? Question 2. Why is a majority required for consensus, and what are the implications of settling for agreement from just one other server? Question 3. Describe how leases facilitate automatic recovery and detail the scenario when a leaseholding server crashes. Question 4. How does Zookeeper achieve leader election using ephemeral sequential nodes? Remember, mastering these concepts is key to robust distributed systems. Congratulations on reaching the final slide of your learning journey. Now it's time to put your newfound knowledge into action. Dive into hands-on practice by implementing a simplified Raft leader election, experimenting with Zookeeper examples, and building a distributed lock using coordination primitives. Don't forget to simulate failures to witness recovery strategies in action. For further exploration, check out the Raft paper and visualization at raft.github.io, delve into Zookeeper documentation and recipes, explore Martin Kleppmann's Designing Data-Intensive Applications, and study papers on Paxos variants and optimizations. These concepts of consensus and coordination are the bedrock for constructing robust, scalable applications. Keep pushing the boundaries and honing your skills in distributed systems. Your journey doesn't end here, it's just the beginning.